if the slides change. Yeah, I've been working on developing these things. Now, these are little boards that make it really easy to develop hardware using JavaScript. Inside them, they've got a microcontroller, that black chip there. So a microcontroller's, it's a completely self-contained computer, really. It's got all the memory it needs, so all the RAM, all the flash. It's got all the voltage regulation and oscillators and everything. You can basically just apply power to this, and it will start running stuff. So this particular one, it's got like 100K of RAM. It's got about 400K of flash. So these are not big numbers, but it's actually a lot. There's an awful lot you can do with it. So these are amazingly popular. They're in absolutely everything because they make it really, really easy to develop all kinds of hardware, much, much easier than using a whole load of analog components. So ARM, who make the core that's in this, who license it, they licensed 15 billion ARM cores in 2015, and they are only one of several manufacturers. So ARM alone have got 2 microcontrollers for every person on the planet produced every year. And these things, anything with a little clicky button like this, so bike lights, key fobs, front doorbells, even things that appear to not do anything at all, like smart cards, will have a microcontroller in, doing a whole load of work behind the scenes. They'll be in your mobile phone, for instance, handling tasks that can be done more efficiently with a microcontroller than with the main processor. So, like on you right now, you probably have a whole bunch of them. So most people will have, if any of you have come across microcontrollers, you will have come across them from this, which is an Arduino board. This is that kind of big black thing there is the microcontroller in this one. All the rest of it is kind of interface so that you can plug it into your computer and so that you can power it from your computer and various other places. So you program Arduinos in C. It looks a bit like this. I'll just give you a really quick demo. So I've got an Arduino board here. So if I go to the IDE, which is not very helpful here, and just click Upload, this is saying, take this particular pin, which the LED's on, turn it into an output, turn it on, wait a second, turn it off, and wait a second. So that's kind of nice and easy, I guess. And you upload it, it compiles it on the computer, and then it sends the binary code onto the board. And hopefully, it'll start flashing, which I'm sure only a few of you can see. So if you get out of this, that's fine for flashing one LED. But what happens if you want to flash 2 LEDs? I mean, you can kind of see how you could copy and paste stuff. But if you want to flash them at different rates, suddenly everything becomes a lot more painful. I mean, there are lots of different ways you could do this. But as you start adding more and more stuff to it, it gets worse and worse. And it makes it very difficult to develop, because you can't just say, I want to use this code to control the display and this code to maybe read the temperature, and just copy and paste them together. Because you've got to fit everything into this loop function that gets called over and over. So, I mean, the other side effect of this is that these Arduino boards, it's very much a black box. So you've sent your binary code over, but if there's a problem, if you get a seg fault or even just like some random programming error, you can't really tell what happened. You can only tell because this LED won't really be doing the right thing. You can put print statements in your code, but then you've got to kind of strip them out when you go to production. And if an error has actually happened that's a bit deeper than that, and your print statement never actually gets to execute, then you're completely stuffed. And you've basically just got to hit undo and keep uploading until it starts working again. So this computer is the BBC Micro. It was released 35 years ago, and it cost £250. So in today's money, it's about $1,500, maybe $2,000. So it's quite expensive. But it had a keyboard, and it had a video output, and you could write code on it in BASIC. And if you had errors, you had syntax errors and stuff, it would actually tell you about it, and you could go and fix it. It happens that you can buy a microcontroller now, that will fit on the tip of your finger, and that microcontroller will cost you under $1, and it's got more power, it's way faster, it's got more RAM. It's like a better machine all round. So why can't we just put an interpreted language like BASIC onto it? Well, you can do, but to be honest, BASIC's looking pretty dated now. If you could put JavaScript onto it, you could do some really cool things. So, JavaScript's already on the server. It's already pre-installed on pretty much any device you have. If you can run it on the microcontroller as well, you can start, say, your Internet of Things device. You can write JavaScript code all the way through. And if you've got some algorithm that was running on the server, you can just transfer that to the client, or you can transfer it to the actual device if maybe you actually want to do more computation on there and reduce the bandwidth of the data that you upload. So this is the Espruino Pico. This is one of the boards that was up there earlier. And yeah, it runs JavaScript. So let's kind of see what that's like to use. So I have here, this is the web IDE. This is actually runs in the Chrome web browser. It's just a Chrome web app using HTML, CSS, JavaScript. But when you install it in Chrome, you get given a few more privileges if you ask for them. And one of those privileges is being able to access a serial port. So when you take the little Espruino board and you plug it in, it appears as a USB communications port. So you can just send characters to and from it. So if I connected this with the web app, and there's the Arduino still in there. Let's get rid of that. OK, so it's come up. We just get a command prompt, basically, a REPL. So when I'm typing characters, those characters are being sent there. The result is being sent back, and it's moving the cursor by kind of standard VT100 terminal codes. So that's pretty standard. You can ask it what its temperature is. And it's got things like command completion and command history built into the little chip. So that's fine. You can get it to turn a light on and off. So we've got digital write, which is the same one we had for Arduino. And we just turn it on. And obviously, we can step up and turn it off. So now if we want to do the blinking light example, we can just do set interval. So that's pretty nasty, and we just have to set up A first. So hopefully we'll see it flashing on and off now. And if we want to flash another light at a different thanks. So if you want to flash another light at a different speed, it's as easy as just changing this and and changing the value that's on there, and it'll be doing the other light, which is a green LED. So what I didn't say is this is all happening kind of in the background. Because you're writing a whole load of small tasks in functions, these are being executed when they need to be because of set interval. But you can still do things on the command line in between. So you can go up and you can edit stuff, and you can kind of change how fast they go and things like that. Now, you might have been wondering what was on the right-hand side there. And that's a standard text editor. So you can whack your code and put it in there. So this is all pretty horrible, actually. But yeah, you get syntax highlighting, you get code completion, and it tells you when you've been an idiot and not put in any semicolons anywhere. So yeah, you can do things like reading data as well. So this is all like a quite nice way to get started. But at the moment, we're not really doing anything. We're not really making anything that you could use. So I've got here a. This is kind of the end of a torch, just jammed into a pipe holder with a little Espruino board on it and a wire here that I'm going to attach to a button. So if I put this in, let's attach it. Oops. So same thing as before, except instead of using the built-in pin LED1, I'm going to use, I think it was B15. So if we do digital write B15, then it'll light the light up. So if we want to do a torch, we're going to need to have a button to turn it on and off. So there's one on the end, which is on pin B3. So I can read the value of B3. Now, at the moment, it should actually be 0. When the button's pressed, it will short the pin to a voltage, and then it'll be forced to read 1. But when there's nothing pressed, the pin's just kind of floating in midair. So it reads kind of random values all the time. So what you need to do is to put a resistor on it. And you could physically solder one, but actually, there's one built into the chip that you can just turn on. So in this case, we'll just use pin mode, B3 and input pull down, to turn on a pull down resistor, which will make sure that it always reads 0. And then if I hold the button and read again, it'll read 1. So we could do something like we did with Arduino, and we could just use set interval, and we could just keep pulling all the time to read the value. But that's going to be really inefficient. It's just wasting time. There's actually hardware inside the chip that actually searches for pin state changes. So the whole computer can just sit there not doing anything until something happens. So that's called setWatch. So let's move this back a bit. Let's just stick it in here. So for setWatch, we actually want to give it some arguments. So we want to say that we want it to always repeat, so it happens more than once. We want to add debounce. So this is a mechanical device, and because microcontrollers run, they're not running super quick. They're running at about 100 megahertz, but that's still more than fast enough to pick up the actual physical contact of the switch bouncing up and down if you press it a bit hard. So we'll wait 50 milliseconds before we actually say this is a press and it's going to do something. And finally, we'll say that we want to only have the rising edge, so when the button is pressed, not when it's released. So let's just take all this stuff out for now. So we've got a function. Let's just write press, just to check it's going to work. And finally, we just need that. So if I upload this, hopefully now when I press the button, it'll say press, which is great. So we can then take maybe this bit of code that we had, just to turn the light on and off, and just whack this in here. We'll set A is 0 again. And obviously we don't want LED 1, we want B15. So if I upload that, and I press the button, hopefully, yeah, it'll turn on or turn off. So now, this is still connected to the computer, but we can save it into memory, and we can end up with a finished device. But it's just a torch at the moment. We could do more interesting things. So maybe we'll just add a strobe to it. So let's keep that. So we'll have a variable called state, and it'll go up between kind of 0 and 3. Well, 0 and 2, and when it hits 2, it'll start flashing. When it's 0, it's off. When it's 1, it'll be on. Wrong way. So I have to apologize. This is really nasty code, but. Right. And finally, we'll just call clear intervals so that each time we get rid of anything that's not needed. Which, if I was doing this properly, we should save the interval. So yeah, if I upload this, hopefully, be able to press the button, and it's not going to work. The what? Sorry. Oh, the digital write. Oh, sorry. Yep. Thanks. Okay. Yeah, okay, so it's on, and then hopefully we'll be able to make it flash. So thanks. Okay, but now it's doing this stuff, we can just type save, and this will actually, it will save an image of the current state of the interpreter into read-only memory. So now we can just kind of unplug it from the power, and we'll just plug it into a battery. And hopefully, if I stuff all of this back in here, we have a kind of working torch that should go through all the different modes of flashing. So that's kind of like... So it's really nice and easy to do these kind of things. So I guess the next thing is, wouldn't it be nice to not make something that runs on its own, but to actually communicate with the PC? So I've got this big red button here, just something that will be a bit more visible. It's got some wires coming out of it. It's got 2 wires to handle a light, and it's got 2 wires for the actual button itself. Now, if we were doing this 20 years ago, the USB spec had just come out, and pretty much every computer had one of these. This was I mean, obviously that's VGA, which is still around, but this is a printer port. And it was meant to drive a printer, and to do it and to keep the hardware simple, it actually output kind of 8 parallel data bits. And you really could just jam stuff straight in the back of it and turn it on and off. So the code for this is Pascal, but it actually looks like this. It's just one line, no libraries, no drivers. It's kind of a bit random magic, but it's writing to that physical port address on the computer and turning on the 8 data lines. It's a bit nasty, and when everyone actually started adding memory protection to the operating systems, it just stopped working completely. But now we're in this situation, and you end up with computers that the only ports they have on them are USB ports. And that's great. It makes everything really nice and easy. But USB is serial data. It's universal serial bus. You can't just take something and plug it straight in there. It's got power, so your USB fans or microwarmers or whatever can run off it. But if you actually want to control something, you need something on the end to interpret the signal. So some of you might have heard of Johnny 5. This uses something called Fermata, which is on the Arduino board. You can just load the software on. And that's actually a really simple command interpreter. It receives commands like turn LED on, turn LED off, read what the signal is, and things like that. So that's great. You can actually write stuff in Node.js, and you can then you can control stuff in the real world from it. But it can't, for instance, if we're flashing a light on and off, you can't say, flash this light on and off. You have to say, turn the light on, turn the light off, turn the light on. So it's really not very efficient or very nice. And you've still got to have gone through and loaded up the Arduino board with the Fermata code first. So let's take a look again at this board. So if I plug in this board, the original one, and I'll just plug in the switch. So, yeah. Right, so we were, when we were connected to this, we were sending individual commands to it. But there's no need to have this web IDE. In actual fact, if I zoom in on this, we can use a standard terminal application. So on Mac, this would be something like Screen, which is built in. On Windows, you'd have to install something like Putty. But so this gives you exactly the same thing on a standard terminal prompt. Oh, yeah, sorry. Okay, so so this is pretty standard. We can do a similar thing, and we can turn the light on and off, which I think in this case is B3. Should work. Yep. But again, we're just sending characters. So if I get out of this and I use echo. So if no one's come across this before, echo is just a shell command that's basically print. It will just write what you give it back out again. But you can pipe it to a certain device. So you can actually pipe this to the TTY device that Esprit is on. And on Windows, this would be like a COM port. And if you do this, in fact, it's already on, so that's not going to work. We can just turn it off again. So now, and you can do this in pretty much any language. You can just open the file and you can start writing to it. But if you're doing it from shell, you can do the kind of command substitution. So $? is the result of executing the last command. Normally it'll be 0 if there's no error, so you won't see anything. But if there's an error, so suppose I just type in something that doesn't work, and then I run it again, it'll turn the light on. So now you could just put this at the end of your build script, and if your build fails, big warning light lights up. So you can do much better than this as well, because you're just sending standard JavaScript commands. You can put a set interval in here and have it do something else, or you can upload JavaScript functions and do all kinds of stuff. But the other side to this is that actually we can go back the other way as well. Now this is kind of super hacky, but so if we go into here and we do setWatch again. And this time we're going to do USB.write to write the data back out without anything else. And this time I'm just going to run the text editor. But so gedit and is just saying in Linux kind of run this as a separate process. So if I attach this to the bin that the button's attached to, again we'll do this repeat true thing. Oops. So now if I press this, hopefully it'll say gedit and. So if I get out of here, actually I can just point the command interpreter bash at this. And now, hopefully, when I press this button, eventually at least, something will come up. So you can do lots of stuff like this. I mean, you could have it going to a web page with the result of doing some analog reading or whatever. I mean, but you can also open the device as a file, and then you can start to read data that's coming straight off it in a much less hacky, more secure kind of way. Because allowing someone to plug any device in and then just get command access probably isn't good. Right. So the other side of this is that we're writing very small little JavaScript functions. So up here, this is a graph of power usage over time. It's a logarithmic scale. So this is actually not on an Esprit board, but it's on another company has made a board called EFM32. So this is drawing 3 microamps, so 3 millionths of an amp. But when it's actually woken up to execute some JavaScript code here, it's drawing about 20 milliamps. So the code is very simple. Every second, it wakes up and it lights up either one LED, the other LED, both LEDs, or nothing. So you can see it here. It's drawing like waking up, executing code, drawing half a milliamp here, doing the same, another one, doing the same, and then 2 LEDs, and it's drawing 1 milliamp here. And then it does the same and drops down to 3 microamps. So that's able to get a sort of 10,000 times difference in the amount of energy it uses just by going to sleep and just by writing pretty much standard JavaScript code. You're not having to worry about power saving at all. It just happens. So if you compare this to something like a Raspberry Pi, this is like a full Linux computer, and it's amazingly powerful. Way more powerful than something like the Esprit board. But you kind of pay for that because you've got half a gigabyte of RAM. That's like 4 billion transistors, and you've got to keep refreshing them every so often. Linux has to wake up to do housekeeping tasks and things. You've got all the extra HDMI and stuff on there. So really, the power usage is not very good. So if you think of this on a 700 milliamp hour battery, that's the kind of battery that's in a Nokia candy bar phone. And Nokia manages to make that phone last for a month and connect to the GSM network all the time. So you run it on a Raspberry Pi, and realistically, you're only looking at 1 or 2 hours out of it. Different Raspberry Pis draw different amounts of power, so you can get a little bit more out of it, but it's never going to last more than a day. And again, with Arduino, you're not looking at a huge amount of power usage either. But Arduino, just because it's not really doing anything most of the time and it can go to sleep, it's able to do really well. So we'll just have a very quick look at this. I've had a little demo. So if I plug this in, okay. So it's a bit blurry here, but you can kind of see that when when the little light's lighting up, it's drawing about 10 milliamps or something. When it's off, it's drawing virtually nothing. But the Arduino is drawing significantly more power, and then when the light goes on, it's even more than that. And this is because the board is not really designed for low power, so that's not helping. Even if you just unplug the chip, it would still be drawing quite a lot. But the chip itself is capable of doing low power, but to get the low power out of it, you have to really know what you're doing with the hardware. You have to read quite a lot of data sheets and actually set up hardware registers and stuff to get it to properly go to sleep and then wake up a few seconds later. So yeah, it's a really huge difference. So all I've done so far is flash lights on and off, which is not really that exciting. This is a picture of things that were supported. That it was taken 3 years ago, and it was stuff that I had kicking around. There are way, way more things in this now. You've got displays, you've got things like GPS, you've got ways to get on the internet. So you've got Wi-Fi, you've got Ethernet you can plug in, you've even got GSM that you can just attach. And all of these things, once you're connected, you've basically got a Node.js-style interface, so you can just request a web page, start a web server, and fiddle around with it while it's running in the same kind of way. So yeah, there's loads of fun stuff. So I'm actually running out of time a bit, but I'll get in something quick. So let's go back to this. So I have here, let's see. Okay, it's a bit of breadboard. You can just literally take things, push them in, and take them out. This is a display that's actually off an old Nokia phone. It's a Nokia 5110, I think. And these are like about $2, I think. And then you've got the little Espruino. So actually, I'll just plug this in. Now, I also have a temperature sensor here, which is, this is like a digital temperature sensor. So there's actually a chip at the end. So you know that there aren't ever going to be any losses kind of down the wire, and you get an accurate temperature out of it. So if I plug this in and want to do something with it, let's get rid of all this code. So on the Espruino site, all of the hardware that's supported, I've tried to make sure it's got kind of a lot of documentation and examples for how to wire it up and do things with it. So if I whack this in here, and it was on pin B4, and now you can just kind of upload it, and hopefully, after a second or so, it'll start reporting the current temperature. But now we can look at the LCD. So this is the LCD. There's a bit of information about it. The wiring's a little different, so there's a tutorial on how to use them on a bit of breadboard. So if we just take this off. And again, we can just copy and paste this code in. And because the wiring is right, this will actually go in. Now, we can't see anything because it's not lit up. So actually here, there's a bit of code for turning on the backlight. And this display is a little bit different. So now you can turn it on, you can see it. So if I copy this code out. So now it's going to be quite easy to just print the temperature. So let's just take this code, really am running out of time, so stick this in here. And yeah, unfortunately, there's a little dodgy character in there because Unicode. Right. So to fixed, we'll make sure it's got 2 decimal places. And if I upload this, hopefully a few seconds later, yep, we'll see the text there, which is tiny. So we can just do set font vector on it. There's a little vector font built into it, so we can kind of very quickly tweak it up. Thanks. So yeah, this is, you can start building things really easily, and I was going to do a little temperature control with it, but yeah, I've basically run out of time. So yeah, just to finish up, this is all open source, both the hardware and the software. I sell these boards, which basically the sales of them pay for the development of the software, but it's available for a whole bunch of other stuff as well. So again, there are way more boards available than this, but like lots of development boards that you can just take it and run it on. Some quite interesting ones are the microbit, which was given to 1 million Year 7 school kids in the United Kingdom earlier this year. And it's got Bluetooth Low Energy on it, so you can start experimenting with Bluetooth Low Energy stuff. And then there are these, which are called the ESP8266. They're about $2 each. They're ridiculously cheap. And they're a little limited, but you can run Espruino on that board, and you can actually have full JavaScript working on this tiny thing that's, I mean, there's no scale there, but it's less than the size of a penny, really. So I'm also going to be crowdfunding this little, it's going to be a little Bluetooth Low Energy device in the next month or so. And yeah, just wanted to finish up by saying that making stuff it's really good fun, and it's nowhere near as hard as you think, especially with the way tools are moving on now. So you should definitely give it a try. If your company's got some little problem, if you've got some issue at home, just have a go at fixing it. It doesn't take long at all. And that's it. Yeah, contact details there. Thanks for listening. Thanks.